Hi guys, so before going to the next chapter, I want to go back to the mirror, to the plane mirror, and I mentioned when I show you like the simulation that if you want to see your full body, you need a mirror about half your height. And I found this picture that explains exactly why. So for example, if you want to see your feet, you see that, so that's just one ray. Okay, remember from an object, you have a bundle of rays, right? You have beam. So you have a ray coming in this direction, that direction, this direction. So I'm just considering this one, and you see that it can reach here the edge of the mirror. So you see that it's bouncing off. So the angle of incidence equals to the angle of reflection. It's going to reach her eyes so she can see her feet. So again, the brain, extend the ray that it gets. And here you have a virtual image, right? Beyond the mirror. And the distance between here and there equals the distance between here and there. Now, if she wants to see the top of her head, no problem as well. You see that the ray is going to bounce off the other edge. And from the point of view of her brain, it seems to come from here, right? So the image will be here. So if you want to have, to save on the size of the mirror, you just get a mirror half your size. So I think I was not clear on that. I wanted to go back to that. The other thing, in one problem we did together, I found a liquid with an index of refraction of 129, and I was not sure what kind of liquid it was. And if you go to that website here, it's called engineeringtoolbox.com, and 1.29, I think you can find it here. Okay, so that will be refrigerant kind of liquid, I'm not sure, but 1.29, yes, we have. So water is 1.33. So this one has an index of refraction smaller, which means the density is smaller. So higher the index of refraction, higher the density, the speed of light will slow down even more. Okay, so then I also want to go back to the simulation about refraction. So let's take this one. And you see this is a ray. So some of it is reflected, some of it is refracted. And if I look at the wave here, so you see here, what you see here are the wave front and the ray that we use in geometrical optics is perpendicular to the wavefront. So what you see as light enters this medium with a larger density, so larger index of refraction, you see that the wavelength gets smaller. And if you do the math, you see that actually the wavelength is divided by 1.5. Okay? So I was not sure I made this clear, but if you have the speed of light is the wavelength times the frequency. The frequency does not change. You see it's red before and it's red inside. So if the speed of light is divided by a factor of 1.5, so then the wavelength is also divided by a factor of 1.5. Okay, so inside the medium, like this, coming from when light goes from air to glass. So let's see, the wavelength is lambda sub 0 in air. So light goes into glass, lambda in glass. It's going to be lambda in air divided by 1.5. Okay? Okay, so what else? I wanted to make that clear here. Also, we always use one ray or two rays but actually rays comes in bundles, right? Just to simplify, we only have one or two rays. And then you see here how rays will refract. Okay, so then before moving on, I have found interesting problem. So it's from your textbook university physics, which is recommended if you are taking calculus-based physics. If you are not taking calculus-based physics, then I recommend physics by Johnson and Cutnell. That's great if you want to take the MCAT. So in this book, there is some calculus. In this book, there is no calculus. Okay, so in that book, there was an interesting problem, I don't know, about the eyes. So let's see. Oh, I don't know, maybe I saved the picture somewhere here. No. Okay, let's try and find it. It's fine. So this is the eye. So here you have your lens, and here you have some kind of liquid. Okay, it's called the aqueous humor, and it's also acting like a lens, right? So it makes sure that your eye can adjust if you are reading a book or if you are looking far away. This one is the one that adjusts the most, and this one is like a fine tune. And this one is attached to some muscles. So if you are reading a book, for example, the muscles are gonna play a role because it will make that lens thicker, so you are able to adjust at a small distance. And if you are looking farther away, the muscle will make the lens thinner, and you will be able to adjust to far away distance. So this here is called the aqueous humor, and it has index of refraction. Since light is going through here, it's going to be refracted inside that medium here. Okay, so the question, and it comes from that book. The book, it's a question I found here in that book. I think it's page from the new edition 1084. So the red light in air has a wavelength of 633 nanometer. So red light is always in that range here, about 0.6 or 0.5 micrometers. So that will be in air. So what you see here, that the wavelength depends on the medium. Right here you see it has a smaller wavelength here in glass, larger wavelength in air. So the wavelength decreases. Okay, so it's given to you that in air the wavelength is 633, but in the aqueous humor, in that liquid here that is part of your eye, the wavelength is 474 nanometer. And the question is, can you find the index of refraction of that in liquid in the eye? And then can you find the speed of light in that medium here, which is part of your eye here, that part here? And then last question is, can you find the frequency? Okay, so you can pause the video and try that. And what is nice is that you go from air, which has an index of 1, to that liquid here. So that means that the wavelength in the eye is just equals to the wavelength in air divided by the index of refraction. Okay, so that works because the index of refraction equals 1. Otherwise you will have to do it differently, but here is straightforward. So then you just plug in, you don't need to, you don't have to convert here. So you do, so you know that you're going to divide, right? So if you go from less dense to more dense, you're going to divide. So for example, if you go from 1.33 to 1.5, you're going to divide, right? So you're going to do 1.5 divided by 1.33, and that will be the factor by which you are dividing the wavelength. Okay, so I wanted to make that sure, so you can pause the video, try to do it. I'm sure you can do it. It's easy. So 474 equals 633 divided by n. And I forget about the units because you have nanometers here and you have nanometers there, right? So you cross multiply. So you cross multiply, divide. So that's going to be 633 divided by 474. And you see that will be the factor by which the index, the wavelength has been divided by. And you get y.34. So you see this liquid is very close to water, okay? It's very watery liquid here. But that will be enough to do the refraction the eye needs. Second question, what's going to be the speed of light in that medium? So the speed of light also is divided by that factor here, 1.34. And we get 2.25 times 10 to the 8 meter per second. So if you want to do a percentage, so you see percentage is 2.25 divided by 3. That's going to be about like water, right? It's about 75%. So it has lost 25% of the speed. It's about the same as water. So the frequency should be still red, okay? So the frequency is by definition the speed divided by the wavelength. Okay, speed is frequency times wavelength. Speed, the speed of a wave, doesn't matter which wave, is also always the frequency times the wavelength. Okay, so that's going to be 2.25 times 10 to the 8. And here I have to be very careful because I have to convert. So that's going to be 474. 4 times 10 to the negative 9. And if you do the math, you get something 10 to the 14. And that will be always, if you have visible light, you always have that kind of frequency here. 4.74 times 10 to the 14. Now, if you look at the frequency in air, so in air of the same beam of light or the same red light, it's going to be 3 times 10 to the 8. And now I have a wavelength of 633 times 10 to the negative 9. And you get also 4.74 times 10 to the 14 hertz. Okay, so the frequency stays the same. Conclusion, if you have, if the index of refraction increases, the speed decreases, the wavelength decreases, but the frequency does not change. Okay, it stays the same. Okay, so now I want to talk about total reflection. So that's going to be the next unit here. Total reflection. It's very interesting. So let's start by using the simulation. So now So let's talk about internal reflection. And let's start with the simulation. So you see here when you go from fast to slow. So here I go from air to glass. You always have a refracted light, okay? Of course, except when it's at, you have 180 degrees here. But otherwise, you always have a reflected beam and a refracted beam. The only thing that will change, for example, it's when you see when the angle is small, I'm going to get large intensity of light here. And when you increase the angle of incidence, you're going to have less intensity here and more there because it has to add up to 100%. But if you imagine that light wants to escape, it can always escape. But now if I have a slower medium here, so here I have glass and here I have air. So now I go from slow to fast. So I go from slow to fast and the beam is always bending, away from the normal. Because you go from slow to fast, so it knows it can take more its time here, so it's refracted or bending away from the normal. So you see here I have an angle of incidence of 30 degrees, no problem, I have a refracted beam. And then I go to 35, no problem. It gets closer, that angle here is the angle of refraction, and it's increasing and it's getting closer to 90 degrees. So look what's going to happen when I'm going to reach 90 degrees. Because it's always bending away from the normal. So it's trying to reach that 90 degrees here that you have here. Okay. So I get to 35. I am at 60 here. I am at 40. See, it gets closer to 90. So what's going to happen then? And then, boom, it disappears. So 40, then I get to 41, poof, it disappears. So at 41 degrees, I'm going to have 90 degrees. Okay, so with an angle of incidence of 41 degrees, the angle of refraction is 90 degrees. And beyond that 41 degrees, poof, it's totally reflected. So it's like light is trapped inside this medium and cannot escape. Okay, it has to go back. So it's bouncing off that border. As I increase the angle, does not help. The light is being reflected until you reach here, 90 degrees here. So it's going to be reflected at an angle of 90 degrees, so it's along the surface. So when I reach that angle of 40, 41, maybe 42, boom, it's reflected. That angle here is called the angle of the critical angle, right? So you have here, the medium here is, you go from N1, which is 1.5, to N2, which is 1. So you go from slower to faster, right? And here, with that angle here equals to the critical angle, the angle of refraction equals 90 degrees. So let's try to find that critical angle here. It's going to be 1.5 sine the critical angle equals 1 times sine 90. And sine 90 is 1. So we have sine of the critical angle equals 1 divided by 1.5. Okay, So you go here 1.5, take the reciprocal, and you take inverse sine here. It's about 42 degrees, okay? So that angle here, when you get to 42 degrees, the refracted angle here is just 90. And for an angle larger than 42 degrees, there is a total reflection. Okay? Now you have the same thing if you go from water. So that means, what does it mean? Conclusion. The critical angle when you go from when you go from glass to air, the critical angle is about 42 degrees. So it depends where you come from and where you are going. So from glass to air, you have 42 degrees. Let's see if you have water. So if you have water, you're still going from slow to fast. But water does not have as much contrast than air and glass. You see, water has a smaller density. So you see, at 42 degrees, you can escape. So you can escape at 10, 20, 30, 40. So it's getting close to 90, but you can escape. Then here you have, disappear, right? So 40, this is 30, 40, 45. Maybe at 45 degrees, boom. Somewhere at 45 degree, boom. It's gonna be boom, disappear. Right? So that's gonna be 40, 45, maybe 47 degrees, something like this, around 47. Let's do the math to find out. So you can pause the video, of course, as usual. So still you go from slower to faster. So that's the condition to trap light, okay? So to have total reflection. So you go from N1 equals 1.33 to N2 equals 1. So the incidence angle here equals the critical angle. So theta 2 equals 90 degrees. So you can have 1.33 sine the critical angle equals 1 times sine 90, which is 1, okay? So let's find out. So you do the same thing as before. You go 1.33. You take the reciprocal, take the inverse sine here. You get 49 degrees, about 49 degrees, right? About almost 90, almost 50. So when you have about 49 degrees here, the beam, it's gonna be along the surface. That will be the critical angle. And if your incidence angle is greater than 49, there will be a total reflection. So I found a video on YouTube and with a demo. I think you can do this demo as well. I don't have an aquarium, so I could not do it, but it's a great demo. It's very nice.
ये है हमारे पास एक लेज़र लाइट, ये है हमारे पास ग्लास और वाटर का सेटअप. मैंने कोई मिरर आपको प्रोवाइड नहीं किया. करना है इस लेज़र यहाँ पर रिफ्लेक्शन शो करें.
So turn off the light.
क्या हो रहा है? नहीं, रिफ्लेक्शन नहीं हो रहा है. आपको सिर्फ वाटर के अंदर लाइटें दिख.
Slow, you go from fast to slow. Light is refracted, but it can escape. Now we're going to go from
अब मैं आपको
water
दिखाता
to
हूँ कि
air.
रिफ्लेक्शन कैसे हो सकता है। देखो ये रे ऑफ लाइट मैंने अब यहाँ पे डाली है, आप देख सकते हो।
Yeah. Isn't that a nice demo? You see how light goes from water to air, and it bounces back. Cannot escape. Try to escape this way, it bounces back. That because you see the angle at which it enters here. Try to this angle here between the normal and that incident beam is larger than 50. If you make it smaller than 50, then you can escape. Here I cannot escape. So it's a very nice.
ये लाइट रे क्या हुई, इधर आई, फिर इधर गई, फिर इधर बाउंस बैक हो रही है मल्टीपल टाइम।
If I have if they had a larger aquarium, it will make the light bounce back and forth, back and forth, back and forth, back and forth forever.
बाउंस बैक हो रही है। क्या यहाँ मिरर लगा हुआ है कोई? नहीं, विदाउट मिरर रिफ्लेक्शन हो रहा है। दैट्स व्हाई दिस फिनोमेना इज नोन एज।
So this is called total reflection. So I thought it was a good demo. So again, here you go from water to air, 15 degrees here, incidence, you get 20 degrees, some of it is reflected, 30 degrees, you get 42 degrees, and then here 45, you can still escape, and all of a sudden, if you are 60, you cannot escape. So in between, you have about an angle of 50 when the angle here is 90 degrees, right? So for 50 critical angle, the angle of refraction is 90 degrees. So the light will go along the surface, and above 50 degrees, you always have total reflection. Okay? Now that's how it works. Here you can, if you have a prism, I can show you that. I can show that demo here. It's a fantastic simulation here. So it's an equilateral triangle. So I cannot do, if I want to do this, I need a prism which is 45, 45, 90. So if you have that, then you see here the angle is smaller, is just 45 degrees. So if you have a prism like this one, which is 45, 45, 90, because of the geometry, the angle of incidence here, so that will be the angle between the normal and the incidence ray is just 45. And 45 is just above the 42 degrees. Okay, we did 42, I think it's not here, but it was about 41, 42 degrees. So 45 is larger than 42, so there is a total reflection. And here we go again. That angle here between the incidence beam and the normal is just 45, which is greater than 41, so you can have a total reflection. And you can use that as a mirror, right? So it means it's better than the mirror because it cannot be damaged as much. Can use that as a way to reflect light. And when you do that, it's called a boroprism. And that is used in, for example, pair of binocular. You see how it's reflected, and then here it's reflected again. Okay, so that means here that will be the distance between two eyes, and here you can have a larger distance. You see how it works. And again, this is because it's a prism which is 90, 45, 45. So the angle here of incidence is just 45 degrees, which is larger than the critical angle. If you have this, that demo I did in class, but it's not 90, 45, 45. So it's trapped, okay, it's bouncing off, but it doesn't go in the same direction. So likewise here, I can do the same here, I can make it trapped if I here, you see it try to escape, it can't, it's bouncing off. But I cannot make it go in the same direction because it's a 60, 60, 60. See here, can kind of make it here. I will show you another demo. But you see how it works. You can play with those tools. This is available here on that website. Okay, so you do have application for that. So if the angle of incidence is smaller than the critical angle, then the beam is refracted and reflected. If the angle of incidence equals to the critical angle, then it's refracted at 90 degrees. And then if the angle of incidence here is larger than the critical angle, so everything is reflected. Okay, so that's how it works. You can see here the same thing. Here it's the computation, but we did that already together. 42 degrees if you go from glass to air. Of course, it depends. It could be like, it could be, for example, you can go from, it's always work when you go from slow to fast. So I can go instead from glass, I can go from glass, to water, okay? There is also a critical angle, but it's not going to be like before, right? So you see here, I still go from slower to faster, but you see that's 40 degrees it can escape. Then you have 50 it can escape, 60 it can escape, and then I increase again, 65 it's gone. So the critical angle is about 62. Okay, again, try to do the math. So you can try to do the math. Again, you go from slower. So this is slower. The index of refraction is 1.5. The angle of incidence, it's the critical angle. Here you have faster, so this is faster. So you have 1.33, and here you have 90 degrees, right? So you can do 1.5 sine the critical angle equals 1.33 sine 90 degrees. Okay, so you have sine of the critical angle equals 1.33 divided by 1.5. You want to make sure it's smaller than 1, otherwise something is wrong. So you go 1.33 divided by 1.5, and you take the inverse sine here, and you get 62.5, okay, about. And that's what you see here, 60 can is, so when it's 62.5, when the angle is 62.5, then the refracted here is 90 degrees. If it's larger, if the angle is larger than 62.5, there is only reflection. So you see here, when the angle is larger than 62.5, maybe it's 65 or 70. So then you have reflection. It cannot escape in to the next medium. Okay, so this is called total reflection. So here we can answer that question here. You can pause the video. So the prism is in prism is a 90, 45, 45, and it's in air. Okay. So you can read the slide and answer the question because we just did that. We just did it, actually. So you see here, the angle here is 45 degree because this is 90. That's a 45 angle. That's an isosceles. Okay, so it cannot escape because the angle of incidence here is smaller than 42 degrees. Is larger, sorry, the opposite. Right, the angle is 42 degrees. Okay, so the angle of incidence is larger. So the incidence is 45 degrees. So it's larger than the critical angle. So if you have glass here and air, glass to air is trapped. Okay, it cannot escape. It's a total reflection. There is no refraction because the angle here is 45, which is larger than the critical angle. But if instead of having air, if now I have my still glass here, but let's say it's water, so it's 1.33 and this is 1.5. Now the critical angle we said is 62 degrees something. So you see that angle here, which is 45 degrees. So the angle of incidence is 45 degrees, is smaller than the critical angle. So what's going to happen? Yes, it can escape, right? So it will escape. So it's going to be refracted toward. So some of it will be escaping, some of it will be reflected. So I don't know where it comes from, that you can ignore that. Okay, so for example, here, you can always reverse a beam. So that means light from the airplane enters the water. That also means that light from the whale escape the water. So the whale can see the airplane, and the airplane, you reverse here, can see the whale. Okay, it's always reversible. So if the airplane is here, so it can see the whale as well. So it means the whale sees the airplane, so you have light coming from the whale, it can be seen by the airplane. If the airplane is further, okay, so now light here, the light that try to reach the airplane here cannot escape. Okay, so it can be, the whale can be seen by the squid here, or it can be seen straight forward here, but it cannot be seen by the airplane. Again, that we just have a few beam, but you have a lot of beam here from light. But if the airplane is at that position here, I cannot see the whale. So that means the whale is invisible, almost totally invisible. So a lot of application for total reflection, and the very important one is optic fibers. So it's like a glass here. It's like a tube made of glass. Those little tubes, I'm sure you have seen those because it's also used for decoration. And you see that visible light here can be trapped inside. Okay, it cannot escape. So it will bounce and bounce and bounce and bounce and bounce and bounce because the angle here for glass to air is about 40 degrees or 42 degrees. So it's always larger than 42 degrees. So why do we use that? We use that to transport information. And why do we want to use light for internet data, for example, instead of radio waves that we use, for example, for communication. It's because there is a principle, and you can look it up. It's from a physicist or scientist named Shannon, and it says that the number of bits, so 0 and 1, the number of bits that you can transport per second. So the rate, okay, it's the rate at which information can be transmitted. So the number of bits per second is the maximum of bits per second will be the frequency of the light you are using. So for example, if you are using red light, the frequency is 10 to the 14, which is 100 terahertz, or 10 to the 14 bits per second. So if you are using visible light, you will be able to transport 10 to the 14 bits per second maximum, but it's already a lot. If instead you are using radio waves is megahertz, gigahertz, so you cannot transport as many bits, right? Because that's principle. It's because you see, you can imagine a wave like up and down, up and down, up and down, up and down. So it could be 1, and then nothing here. It could be a 0, and then 1 here, and then nothing here. It's going to be a 0. So the maximum data you can transport. So here nothing can be a 0, and then here you have a 1. So here there is nothing here. The maximum will be the number of bits that you can transport. Of course, it's going to be the frequency of the light you are using as a carrier to carry the information. So you can carry a lot more information if you are using visible light. So that's how it's used, right? So you are not losing energy here. You are not losing your information. You are not losing your bits, because light keep bouncing inside that fibers here. Okay. Sometimes when we use our cell phone, for example, they are using radio wave. Okay, so radio wave can carry a sound wave, so that will be the sound. For example, when I talk into my phone, to carry that information here, I'm gonna use radio wave, okay, which is the carrier. But if you want to use more information, radio waves are not, or microwaves don't have enough frequency. So instead, I can use visible light. So that's an application. Another application in the same idea will be endoscopy. So you have all kinds of endoscopy. So for example, you can look in the stomach, what's going on here, and you have a small camera, and that's because light here coming, it's going to be trapped inside that tube. It's going to be reflected. You have total reflection. And you can even use endoscopy with a very small fiber here to study the capillary system. So that's also used for that. Another advantage here is that the fibers are so small, so tiny, that you can, in one cable, you can have more than one fiber. So for example, if you are talking about a phone line, you can have more than one phone line. So this is also an example, interesting example, how that total reflection is used. And it comes from the book I was talking about that I recommend the reading. It's a conceptual, it's called Physics Behind the Headlines, or Physics for Future President. Here. So that's a very interesting book. So in the ocean, So not only light can be reflected, right? Not only light can be trapped inside the channel, but sound also can be trapped because it's also a wave, so it has the same properties. So in the ocean, you have here, it's going to be warmer, right? And here you go down, the water is getting cool, you're gonna go even down more. Okay, so you increase the depth. What's going to happen? You increase the pressure. So we talked about that last time. If it's warm, that means the molecules are moving faster, so the sound can move faster. But if you increase the pressure, that means the molecules are closer to each other. So for example, sound will move faster in a liquid or in a like remember in the cowboys, if you watch cowboy movie, you see people putting their ears to the railroad because the sound will move faster in the railroad um, track than it's moving in air. So you will hear the train ahead of time if you put your ear on the uh, train track. If you put your ear on the track because it's metal. So more pressure means that the sound will move faster. So if you have, for example, two waves far away, maybe this one is chilling in Florida, this one is still in the North Hemisphere, somewhere in the Arctic, they can talk to each other using that very special zone. We call that the sound channel because here you have fast and here you have slow and here you have fast again because the sound travel faster here than here. So when a sound is emitted, it's going to be totally reflected. It's being trapped inside that channel. Okay. And the sound does not lose its energy, doesn't spread out in 3 dimensions. So there is not this inverse square effect, right? When you talk, the sound goes in 3 dimensions, so you are losing the energy. Here, the energy is not lost, it's going to be trapped. And there is this book called Red October. There is also a movie. And I think it was during the Cold War, the submarine, they knew how to use the sound channel because if there is a submarine here making noise, the noise cannot escape. So it goes undetected, right? It was kind of classified for a while, but it's a known fact that submarine, if they want to go undetected, they can travel through that sound channel. So that's interesting. Also, here it's also a very nice story that happened in the Cold War as well. So the Americans were trying to spy on the Soviet Union. It was the time of maybe Stalin, and they wanted to. So both of them had the technology to make a hydrogen bomb. Okay, after the Second War, they developed the hydrogen bomb, and the American wanted to know if there was some explosion happening in the Soviet Union, if they were trying to test the bomb, if they were doing nuclear reaction. So they had the idea to put a microphone, and at the time the microphone looked like a disc. Okay, it was before all the technology that we have today. It was before the transistor and the semiconductor. So microphones were very bulky. You see that in the old movie when they talk in a microphone, it was all flat and it was big. So they had the idea to attach the microphone here on a hot balloon. It was classified, of course, and they were using a sound channel that exists in the atmosphere. So here you have warmer air because the molecules here are ionized, so it's going to be the ozone layer. Here you have warmer because you are close to the earth, and here it's cooler. So the sound can be trapped inside that sound channel into the atmosphere. So if you put a microphone, and that's what they did, they could spy on the Russian. So they could spy on the Soviet Union, right? So there was an explosion. The noise here will be typical, will be trapped inside that sound channel, and you can collect that sound here. And one day the balloon crashed, and then it went unclassified. It was classified for a time, and it just crashed next to a military base in Roswell, New Mexico, and people spotted the dish here. So they said, "Oh, it's a UFO," and that's how came the story about Roswell. You see, the people were seeing that disc here, and they thought they were UFO, and it was in the news all over. And of course, the military didn't want to say what it was, so they say, "Oh yes, maybe there was a UFO." It's not like the history doesn't repeat itself. Like recently, we had also some discussion about UFO, and then it was classified years and years later. Okay, but that's how the story about Roswell came about, and there was a museum here that you can visit. So I'm not sure why the the alien looks like this. I don't know why they decided they had to be green, but that's the story about Roswell. So interesting story. So I hope the video is not too long. Okay, so interestingly about diamonds. So diamond, they have a very high index of refraction. So so the diamond, I think it's about 2.42. So if you want to go find the critical angle for diamond to air, it's going to be a very small angle. Okay, you can do the math. It's going to be 2.42. You take the reciprocal, you take the inverse sine here, and you get 24 degrees, about 25 degrees, right? So if the angle of incidence is smaller than 25 degrees, it's going to be total reflection. So that makes the diamond very shiny because white light enters the diamond, and then it's always, and especially when it's cut, right? It's cut in such a way, the angle of incidence is always larger than 25 degrees. So it bounces and bounces and bounces and bounces and bounces off. When finally it exits, depending on the index here of refraction of the diamond, it's gonna also be you're gonna also have colors, right? You're gonna have the rainbow because we're gonna see that light. The refraction, the angle of refraction when you go from slow to fast. Finally, when the angle here is smaller than 25, the refraction here depends on the color. So it means that blue light will be refracted more than red light. Okay, so it depends on the wavelength. So blue light has a smaller wavelength, larger frequency, so it's going to be refracted more than red light because the speed for blue will be smaller than for red inside the medium. So that will make this beautiful color of diamond, and each diamond has a specific rainbow color. Here you have pink diamond, you have blue diamond, and the other thing is that you have a large dispersion. Okay, so if you just have glass, you can have a small rainbow, but for diamond, you have very large dispersion here. So the difference between red and blue for the refraction will be very large for diamond. And of course, it's recommended to buy zirconium because you don't know where the diamond comes from. But that's a parenthesis. Okay, so we did so 28 degrees. So you can pause the video again, but 28 degrees, you see, it's an angle which is larger than 25. So light will be trapped. Now, if you go from diamond to water, so then light can escape. Okay, so let's see if we go from diamond. If you go from diamond to water, what's the critical angle? So here you have, I think it's 2.42. Here you have 1.33. So you go from slower to faster. So you're going to have 2.42 sine the critical angle equals 1.33 times 1. So you can find the new critical angle. And you get, so 1.33 divided by 2.42. You take the inverse sine and you get 33 degrees. 42. So the critical angles is about 33 degrees. And you see that 28 is smaller than the critical angle, so it can escape. Okay, so that's that problems here come from the book Johnson and Cutnell. So it's an algebra-based book, and it's a very good textbook if you want to review your MCATs. Okay, did I cover everything here? So one more thing, I think it's I hope it's not too long. So you can see here. Oh, that's some problem. I think you can do that on your own. We can try to do number 3. What index of refraction must a transparent material have in order for the total internal reflection to take place at all angles larger than 50 degrees? So you go from slow n to fast. So we suppose that fast you have 1 and you try to find n. So that means the critical angle equals 50 degrees. So that means that n sine 50 equals 1 times sine 90. Okay, so you can do the computation. I think I did it. I found 1.31. Okay, so if the angle of incidence, so incidence is smaller than 50 degrees, so then yes, it escapes. You can have refraction plus reflection. If the angle is larger than 50 degrees, then it's trapped. You have total reflection. Okay? Diamond is 25. And I think we did already a lot of those problems here. Water to air, we said it's about 49 degrees. Water to air, right? We did that. I think we did it class before. Water, if you go from water and you go to air, it's about 49. Okay, 30 you escape, 40 you escape, 45, boom. So it's about 49 degrees. Okay, 49 degrees. That's what it means here, but 49 degrees. Okay. There was a 49 degrees somewhere, but that's where it comes Okay, so the last part is it's called dispersion. It's when you have a rainbow, right? So it means that white light is actually made of all the colors of the rainbow. So you have a blue and red and yellow all mixed together. And the refraction depends on the wavelength inside glass here, depends on the wavelength. The index of refraction depends on the wavelength. So that means blue, for blue, the index of refraction of that glass is not going to be the same as red. So it means blue or purple or smaller the wavelength is, more refracted it's going to be. And that difference here, that differential here, that's going to give you the dispersion. And in diamond, you have a very large dispersion. It depends on the glass here. So for example, if you usually have a crowned glass, and you can have a nice rainbow. So for example, small. Here you have a small demo. You can buy a prism here, very cheap from the internet. It's made of ground glass. You do that demo in the morning, right? When light will shine here on your prism, and you get a rainbow. You see here you have red, yellow, green, blue, purple. Here you're gonna have UV that you cannot see. And here you have infrared that you cannot see either. But if you want to do a cool demonstration, and that was done by William Herschel, the first to do it. Maybe not the first, but the one that reported that finding. If you take a thermometer here, you're going to see that the thermometer will increase because here you have infrared, and infrared is a heat wave. So here you have some infrared that you cannot see, but if you put a thermometer here, you should see the temperature changing, and here the temperature does not change. You can also make a rainbow very cheaply just with a bottle here. Here, if you just have a bottle here, has a bottle with a right angle, like they do sometimes, and you can see the rainbow here as well. I don't know if you want to see the shape of the bottle is not round, it cannot be round. It's kind of has a square base here. That's how you can get a prism. It can work like a prism. You can do the rainbow also if you with this. I think if you take, so this is red, okay? So with red, of course, you cannot have a rainbow because it's red light. You can have blue light, and you see that for this material here, red here will be refracted, but blue, if I take blue, you see there will be more refraction. So if you can see that, I can take this instead. So this is blue, so you're gonna have some refraction here, and if you take red, you have less refraction. It was better seen here. With this one, you can see that. If you see blue, and then red, if you take red instead, up, it's moving a little bit in this direction, so it's not going to be refracted the same. So the index of refraction, so it means the factor by which the speed is divided by depends on the wavelength. And you can also see that here, if you do wave here, and if you go from, for example, air to glass, you see the wavelength gets smaller. And if you take blue, the wavelength gets even smaller, right? So blue will have a smaller wavelength than red inside the medium here. You see the wavelength will be the distance between two crests. These are wave fronts. And if you take blue here, the wavelength are smaller. I hope you can see that. So that means the speed of light for blue will be smaller than for red inside that medium. Okay, so I don't know if I have see here red, that will be the wavelength in a vacuum and index of refraction. But if you have, for example, blue, you have a smaller wavelength, the index of refraction will be larger. So that's going to be for ground glass. So it means that the speed of light for blue inside that glass will be smaller than for red. So the index of refraction is a function of the wavelength, or the wavelength is a function of the index of refraction. So you can see that here. You see blue or violet is more refracted than red here, and the wavelength, of course, is different. So that's interesting. The distance here will be called the dispersion. And for a diamond, so it depends on the material. So if here it's just for a ground glass, but if you take a diamond instead, you will have more difference between red and blue when it comes to the index of refraction. So you have more dispersion for a diamond. That makes the diamond even more interesting. Okay, so the first one to talk about that was Newton. He did this experiment and he was able to show that white light coming from the sun, he has a hole here in his blind. His it goes for a prism, and he was able to show the rainbow. And this is William Herschel, and he got the idea to have a thermometer here, thermometer next to the red here, that's red, and here you have infrared, and he was able to show that thermometer will the temperature shown by the thermometer will go up. Okay. Okay, so we can also explain that phenomenon when the refraction depends on the wavelength. Is also why do we have rainbow? Because water droplet will be like prism, right? So you have blue here and you have red. So you have all the color of the rainbow, but each droplet in the sky, they do all the same thing. So you have all the red here coming out of the raindrop at the same angle. So they will build up on each other. So you have a lot of red here in this direction. In that direction, you have a lot of blue. Okay, so I think I have an arc to show you that. Let's see. So let's take a raindrop here. And because it's raining, maybe. And this is the light from the sun. And I thought it would be easier to show you. Okay, you can kind of see here some of it is reflected, some of it is refracted, so you can have blue more refracted than red. I thought I had a better. Let's go back. No, I thought I had a better simulation, but no, not great. Ah, yes. Okay, that's your raindrop here. And now this is what's happening. Okay, so this is the light from the sun. It's gonna enter, go from fast to slow. When it wants to leave, right, it's gonna be trapped inside the raindrop. Okay, it's spherical, cannot escape because the angle is not right. And here you have refraction. So you're going to see in this direction, you're going to see blue. In that direction, you're going to see red. But because you have a lot of drops, all the red will be refracted in the same direction. So you have constructive interference. All the red will pile up and all the blue will pile up. So that's what you see. So you can do your own research about formation of rainbow because it's very interesting, but that's the idea. You have also kind of the same thing when you have a DVD or oil on water. You see, you're going to have refraction here, but you're going to have a lot of refraction and you also have a dispersion. So you have refraction and dispersion. So all the blue will be refracted in the same direction. All the red will be refracted in the same direction. So that's why you're going to have a rainbow. Okay. So you have like three things at the same time. You have refraction. You go from oil to air. Then you have rainbow because blue will be more refracted than red. And then you have all the red piling up together, which is constructive interference, and all the blue piling up constructive interference, and that's why you get a rainbow. You also get a rainbow when you have oil on water. Okay, so that's how it works. You can see here red always in the same direction. So you're going to see red here, blue always in the same direction, refracted in the same direction because they are all the same water, it's the same medium. So you're going to see your violet from in that direction. So it's like a virtual image. Okay?